We're very excited to have Bob here with us. He's one of the content creators for CCAR. I'll let him tell you a little bit about CCAR. He knows it much better than I do. But to give you a little bit of a background on Bob, he spent quite a few years as a master technician, diesel technician for Ford, and but for the past several years, he's been with CCAR writing a lot of the content that you might be familiar with if you use Electude. So all of their content is provided, all of their safety content is created by Bob McGinn and the other fellows at CCAR. So without that.
Hold on one second, Jake, before you cut loose of the intro. PowerPoint, as typical, will choose to defy me right now, and I need to restart it.
Okay.
Unbelievable.
No worries, Bob.
Okay, that's in. Now let me go back and select that screen. Great, Teams has got it reversed. You seeing my notes page, I imagine?
Yep. Give me just 1 second, I'll send it live.
Oh, hold on, let me reverse that. So now you have the presentation page?
Yep, looks good to me. You ready?
Sure.
Off we go.
Bob, that little Teams thing in the corner of your window, if you just hit the minus, it'll disappear.
The what?
There's a little Teams pop out we're seeing there.
Oh, okay. Is that showing up on the?
Yeah, just hit the minus in the corner of it and it'll go away.
Okay. Very good. Technical difficulties have now been done. Okay, so good afternoon. My name is Bob and I am with CCAR, and you're here for hybrid and battery electric vehicle safe handling and best practices. If not, you're maybe in the wrong place. Presented by Electude and the Coordinating Committee for Automotive Repair, as I prefer to call us, CCAR. Before we get going, we need to cover the standard disclaimer, which I'll distill down to a few very simple sentences, which means I am not a lawyer or a doctor. You might be. Anything that comes out of my mouth should not be construed as medical or legal advice. In any case of any question, please seek out the local authority in your jurisdiction. So a little background. CCAR formed in 1994. The initial fundings were provided from the US EPA. They were able to stand up on their own, be self-sufficient in the early 2000s, and since have signed multiple alliance agreements with US OSHA. We are now on our way to becoming an OSHA ambassador. We were chosen by a group called NAHAC to develop a line of hazmat training for dealerships in 2005. We partnered with our friends at Electude to distribute the e-safety product, which is what this presentation is based directly out of, is the content for hybrid and battery electric safety that you find in the CCAR e-safety product housed in Electude. We're based in the Chicago area, and our sole focus is the automotive industry. Our friends Electude, founded in 1990 by two geniuses, really extraordinary system, world's leading automotive e-learning solution used by thousands of schools. It's cloud-based. They partner with us to provide e-safety. By the numbers, and these numbers are all gone now because of the COVID thing, there are more languages, more users, more instructors, more schools in more countries. Then there's me, over 35 years, technician or technical specialist, 25 years in heavy, former master certified for engine chassis and diesel powertrain. I still have current ASEs for L1, L2, L3. I am a recovering wrench, I'll admit to it. I've been recovering since July of 2017, joined CCAR in August. So I'm coming up on my 3-year anniversary. And I am the content developer of eSafety, that enormous amount of safety content. Nobody thought it could ever be that big. That's housed on the Electude platform. And if you don't like the presentation, get in touch with me afterwards. We'll see what that gets you. So this course is basically designed as safety concepts for the compromised, not for normal vehicles. This course does not address normal handling or diagnostics. We will not address any manufacturer tier 1 supplier issues. We will limit the discussion to personal protective equipment, isolation, and vehicle fires. So, how does this affect you? A couple of questions we need to ask. So whether or not you're currently teaching electric drive, at some time in the future, you will likely have a hybrid or battery electric brought into your shop. Might be the daily driver of a coworker, or might be a new acquisition by an up-and-coming and enthusiastic student that back in my day we referred to as a gearhead. You may have collision techs in your program. If your gearhead, your collision techs, your coworker, or even you have found a second car or some other car that is not brand new, that's like my first car was, which was a rusted out wreck ready for the scrap heap, that's what you got. But if that's a hybrid or an electric vehicle, there is a potential problem and you may have a potential hazard on your hands. Now, hybrids and electrics have been around more than 20 years. Today, it's estimated there's close to 3.85 million traveling the roadways worldwide. HEVs and EVs offer substantial increases in fuel economy and greatly reduce or have a great potential to reduce greenhouse gas emissions as the source emitter. Important to qualify that, only as the source emitter. To achieve these goals, you'll use extremely different and complex powertrain components and strategies compared to those used in traditional ICE engines. But central to all platforms is a storage battery of some type, whether that is lithium-ion or nickel metal hydride. And the unique operating characteristics of hybrid and electrics present a unique set of hazards that need to be understood by technicians before diagnosis begins. Now, in the course of a normal day-to-day, hybrids and electrics pose no greater risk than traditional ICE powertrains. However, when extraordinary events such as a collision, fire, flooding, or containment penetration of the high voltage battery occurs, it may start in motion a series of events that can be extremely dangerous. I may use the term extraordinary event. I'm referring to things that aren't necessarily collision, like possibly minor grounding of the chassis from hitting a pothole. And technically, it's a collision with the roadway, but let's talk about something along the lines of a cooling system failure at the physical level within the battery pack system that the electronic system hasn't caught up with yet. Extraordinary event. When such an event occurs, the vehicle's protection strategy typically executes to prevent possible electric shock and fire hazard exposure to the occupants. Anyone know what some of those strategies are? I think you do. It would be things like opening traction battery contacts. If we have a hybrid, we would disable the fuel system, which leads to the condition that is present when this occurs, which is stranded energy. Stranded energy defined here, the inability to remove stored energy from the battery pack after a collision event. The remaining energy in a high voltage battery presents two hazards to anyone in contact with the vehicle. That's first responders on the scene, or later on vehicle technicians get a hold of it. And the first is from electric shock from either battery chemistry, either lithium or nickel metal hydride. And the second is fire from lithium. Electric shock hazards may be present after an extraordinary event, such as a breach or damage, crack or puncture. Technicians should always approach a hybrid or electric that has been involved in a collision or other extraordinary event with the mindset the high voltage battery poses an imminent danger of electric shock and is unstable until a detailed inspection of components indicates otherwise. Both lithium and nickel metal have the capability of producing extremely high voltages. Contact with any protruding object must be avoided. Can't stress that enough. When the battery type involved is lithium ion, particular attention should be paid to the following possible conditions. Things like popping, leaking or dripping from the battery area, smoke or hissing, or sparks, because they probably mean something. Now, if a vehicle is involved in some sort of extraordinary event or collision and found to have damage to that lithium ion battery case and has not yet experienced its thermal event, and by thermal event, I do mean fire, then precautions including isolating the vehicle outside at least 50 feet away from any other flammable combustible material must be put into effect. And we'll find out why in a minute. The battery should be monitored with thermal imaging equipment or a non-contact infrared thermometer for a sufficient period to determine if the battery is getting warmer or cooler over time. Once it's been determined that the battery is temperature is trending at a stable ambient or is actually cooler than ambient, it's possible to address further repair operations. Getting warmer above ambient, and that is possible, is not a good thing. Here another disclaimer where we're telling you basically it is strongly recommended that the OEMs document a repair procedure for handling a damaged or compromised high voltage battery must be followed if available. If necessary, contact your OEM directly for technical assistance. If you're attempting to remove a damaged high voltage battery from a vehicle, the process should be monitored continuously for changes in the battery's thermal state, with the expectation that an unstable lithium ion battery could develop a thermal event at any time. And if you're successful in getting a battery out of a vehicle, we would appreciate it if you would isolate that battery outside, away from people, away from flammables, hopefully protect it from the weather, a shed, a tent, something to keep the prying eyes and the general public away from it until it can be scrapped to the authority in your jurisdiction. So, why all the bluster about lithium ion and fire? Why the isolation? Why the temperature monitoring? Is this guy a lunatic? Not necessarily. It's because of thermal runaway. Thermal runaway describes a process which is accelerated by increased temperature, in turn releasing energy that further increases the temperature. Now, I will repeat that because thermal runaway describes a process which is accelerated by increased temperature, in turn releasing energy that further increases the temperature, or a thermal chain reaction, if you will. Thermal runaway event can take place as a result of any of the following conditions. That could be physical damage, something happened to the battery case and actually made contact with internal battery cells, water intrusions with a battery if somebody decided they were going to try and jump the lake and didn't make it, or ignition of the battery after a fire that may not be its fault in the first place, a collision event that ignites liquid fuel that has heated the battery sufficiently and now has compromised that battery. So if you experience popping, leaking, dripping, smoke or hissing or sparks in the battery area, you may be a thermal runaway. And because it's the gift that keeps on giving, there is no time limit on how long it takes for a thermal runaway event to occur. Thermal runaway event could take weeks to occur after collision or extraordinary event. Reignition may occur, or ignition in the first place, may occur at any time without warning. That is why we say, until you are certain of the condition of that battery, leave that vehicle parked outside 50 feet from any structure, person, or combustible. Right now, it's time for a quick word about firefighting. So those of you in post-secondary that may have fire sciences or future firefighters in training as part of your course offerings, you have a different take on this. But primarily, we're telling everybody that once a thermal runaway event resulting in a reignition has occurred, it's not easily going to be extinguished. Firefighting operations may require in excess of 2,500 gallons of water to sufficiently cool and extinguish a high-capacity lithium-ion battery. Your use of firefighting agents such as the Class A, B, C, D foam or halon simply do not possess the cooling ability or the heat sink ability of water. We're not looking to remove the oxygen here, and we'll get to that in a minute. We are looking to lower the temperature. If you have an ignition that develops into a fully involved battery fire and that vehicle is in the building, it will most likely require calling the fire department to handle that fire. Be prepared to evacuate. Don't try and fight it off with a garden hose. Which brings us back to those of you that may have fire sciences candidates. If they have full turnout gear and they have basically all of the same equipment that they would have if they were part of an actual fire company, let them have at it. It's probably good practice. But make sure everybody is out of the building other than them, and they have to be dressed down for contained air. Scott air packs are equivalent, because the fumes that are going to be floating around are noxious and extremely deadly. And as a further complication, hybrids will have gasoline. For this reason, careful consideration must be given to the reduction or isolation of a hybrid vehicle's liquid fuel charge, if possible, to prevent catastrophic loss of life and property damage. It's for this reason that we're saying that it may not be possible to conduct repair operations on a damaged hybrid safely. In this scenario, if that battery is getting warmer and you can't get the fuel out of it in enough time, push it out the door. This would be a good time to stop and see if we have any questions. And I don't know who's covering questions right now.
We're looking here, Bob. I don't see any questions come up. There's some new ones here.
No, if not, that's fine. We can move on, and that will.
Yeah, I don't see any here.
Very good. So, systems are generally designed to be tolerant of abusive conditions such as overcharge, short circuit, crush, fire, exposure, overdischarge, or mechanical shock and vibration. The propagation of thermal runaway from cell to cell can lead to a cascading failure of a battery that will result in a fire and can be extremely difficult to extinguish. I don't know, is the camera still on with me, Jake? I just want to hold something up for people to see it.
Yep, we can see.
What I'm referring to is that in this instance, what I'm holding up in front of the camera, you see a Rayovac next to an 18650 battery. This 18650 and then further on the newer 21700s were the batteries primarily used by Tesla. And there's 4,000 or 5,000 of those 18650s in the original Roadsters. So regardless of whether or not that cell is or that pack is built up of any of the aforementioned or the pouch and prismatics, it's important to remember that batteries contain both an oxidizer in the form of a cathode and fuel in the form of an anode in a sealed container. So when we have a oxidizer and a fuel in the same compartment, we don't need any oxygen.
Bob, could you hold that up again real quick?
Sure.
Kind of in the tiny screen there. You held it up at first.
There. Hopefully that's coming in okay. This is just to give you a size reference on what we're talking about inside some of these batteries. Now, this is old technology, and this is an original LCO, which I'll get to in a second. It's the next slide up, type of cell. So you can switch me off. That's all I really wanted to show the group. So, and it brings us right here to, so moving forward, let's identify some of the chemistries out there in the powertrains. All the players listed here are cathodes except for the lithium titanate. And you have things like nickel manganese cobalt that's used in the Leaf and the Volt, nickel cobalt aluminum. We are dropping the lithium off the front end of it because lithium is involved everywhere here. Titanate used in the IMEV, the FIT, and also part of the nickel metal cobalt cathode. Lithium cobalt oxide, the one on the bottom, is the original lithium ion original gangster used in the Tesla Roadster and the Smart 4.2. So under normal circumstances, fuel and oxidizer will convert stored energy electrochemically, chemical to electrical energy conversion. If the electrode materials are allowed to react chemically, that might be because of a puncture or some contact that crushes that cell. And now we have these two substances in contact with each other. The fuel and the oxidizer convert the chemical energy directly into heat and gas. Once started, this chemical reaction will likely proceed to a completion because of direct contact of the fuel and oxidizer becoming exothermic, thermal runaway. And once it starts, as we have said before, it can be extremely difficult, if not impossible, to extinguish. So just to include a little more confusion, a little added science, but there's no test and we don't need you to do any math. But on the high end of the scale, lithium-ion batteries have a specific energy in the range of, pick the units that you choose to work with. I like 185 to 200 watts per kilogram, watt hours per kilogram, excuse me. This is the electrical energy they support, or how much juice they can hold. This is sometimes referred to as energy density, but that's volumetric, and we're talking about mass in this instance. Now, depending upon the type of cell, the chemistry, which we just saw on the previous page, the electrolyte, which is extremely important in that equation, but most importantly, the state of charge. How charged was the battery at the time? The enthalpy of combustion, or what's known as heat of combustion, can range in the area of 1388 to 5500 watt hours a kilo. This is its capacity to release heat in an exothermal event, a fire, how big of a bonfire they can become. So if you gain nothing else from the man with his hair on fire, raging with fire and brimstone about the potential hazards, it's this. All chemistries have the potential to release much larger quantities of heat compared to their electrical energy if they are on fire. And the higher the state of charge, the higher the heat release rate. Some tests had the 18650 with a single 18650 in the range of 5.2 to 8.3 kilojoules, and kilojoules and watts are interchangeable in this instance, per second. The higher the state of charge, the sooner a thermal runaway will begin. So I threw in a new term, heat release rate, and just so everyone's clear, we use the birthday candle example here, where one candle burns at approximately 1600 degrees F, and it releases maybe 60 watts of heat energy a second. Now, if we bundle 10 of them together, tie them with a rubber band, light the flame, and they're all burning as one flame in unison, it's still going to be 1600 degrees, but now the heat release rate is 600 watts a second. So we cleared up what heat release rate was. So failure modes. The failure modes of any lithium-ion cell that can lead to a thermal runaway event may be categorized into three major groups: thermal instability, electrical, and mechanical. And the things that come to mind for thermal are things like fire due to gasoline, or some other elevated storage temperature or elevated temperature event that's not the fault of the battery. Could be overheating due to a rapid charge or discharge, thermal shock cycling. Electrical instability could be an overcharge or an overvoltage, a short circuit, over discharge, or too rapid of a discharge rate, or how about a polarity reversal? Something happening that causes, we all know what happens when we put the jumper cables on backwards. Mechanical is simply crush, penetration, drop, immersion, vibration, mechanical shock. And I'll let you know a little secret as we move up, because there'll be a few plots coming up that have a couple of numbers, but nothing to freak out about. The magic number to research appears to be around 350 to 392 degrees F, somewhere in that range, to trigger a thermal runaway event. And that will be based on what the chemistry is and the state of charge. That temperature is probably going to pop up. Also remember 190 to 200 degrees Celsius, because it is a Celsius chart I'm going to show you. To further understand thermal runaway, it's essential to grasp this concept also, and that is that heat generation increases exponentially within the battery while with temperature, while heat dissipation, or the ability to, it says increases, but that's just because it's on a plot, the ability to cool it is a linear or gradually over time. The response to any failure mode scenario arises from the dynamics of heat generation and heat dissipation over time. So faults and outcomes. When a battery pack or module fails, the resulting outcome will fall into one of three categories: preferred, unacceptable, and acceptable. We're going to take a quick look at each one to see what those scenarios might look like. First up is the preferred outcome. in this case, we'll describe it as failure that occurs within the cell that leads to an increase in temperature. Pick the favorite failure that you like. I happen to like short circuit. A reaction within the cell creates additional heat and gas and the reaction zone expands. But in this particular instance, the heat dissipation rate exceeds the generation rate over time and the cell is cooled. A benign temporary thermal event, no thermal runaway. What I was talking about as far as plots, when you look at the plot that's on the screen right now, you have an area that we're calling the heating area is called cooling. And the slope of those curves is very close. They're not exact, but they're very close. So that's telling us for as much heat, we have the ability to cool as much. Probably looks something like this. If you haven't figured it out already, but I bet you have because you're a smart group of people, that this is my poor attempt at a thermal scan. Not much to look at there, just scorch the case a little bit. So to recap, failure occurs within the cell. It leads to an increase in temperature. I like short circuit for a failure. Reaction within that cell creates additional heat and gas, and as the reaction zone expands, the heat dissipation rate exceeds the generation rate and the cell is cooled. No thermal runaway. So up next is an acceptable outcome. And here, before we go to the synopsis, we'll just take a look at that plot. Here we see in the area labeled heating that curve is off to the races and has peaked and is on its way down, where cooling is lagging behind considerably. And in this instance, for an acceptable, we're going to say that failure occurs within the cell that leads to an increase in temperature. Let's go with overcharge. Reaction within the cell creates additional heat and gas. The reaction zone expands. Heat dissipation rate is less than the heat generation rate, and the cell enters thermal runaway. Additional heat and gas are produced. The cell vents, possibly explodes, but nearby cells heat up, but not driven to the point of thermal runaway. The expansion of the failure is stopped at the initial cell. Probably going to look something like this. And once again, my poor attempt at thermal scan, or you can think of it as clown makeup. That one we let the smoke out. And at the same time, we scorch that battery. So to recap, failure occurs within the cell that leads to an increase in temperature from overcharge. Okay, I'm good with that. Reaction within the cell creates additional heat and gas and the reaction zone expands. Heat dissipation rate is less than the heat generation rate and the cell enters thermal runaway. Additional heat and gas are produced, the cell vents and explodes. Nearby cells heat up but are not driven to thermal runaway, and the expansion is stopped at the initial cell, which brings us to the unacceptable outcome. And before we utter a word, I would ask you to take a quick look at that plot, because that plot is different. That plot has numbers on it. And across the x-axis, we have the battery pack's temperature, mean temperature, in degrees Celsius. And on the vertical, we have the heating rate in degrees Celsius per minute. And as we mosey out from 100 to 150, we're heating at about a half a degree to a degree a minute till we hit the onset point. And then from 150 up to about 175, 180, we're jumping up at 2, 3, 4, and finally up to 5 degrees a minute that we are heating until we hit 190 degrees, and then it goes straight vertical. You're looking at a graphic representation of thermal runaway. Temperature that is rising at some steady and measurable rate, and that at some point, wherever it decides to, it goes vertical, and it is the point of no return. And in this instance, we would describe this as an abuse event that occurs within the cell that leads to an increase in temperature. Here we're going to say that this is due to some sort of mechanical crush penetration. Reaction within that cell creates additional heat and gas and the reaction zone expands. Here the heat dissipation rate is substantially less than the heat generation rate over time, and the cell enters thermal runaway. Additional heat and gas are produced. The cell vents violently and it explodes. Adjacent cells are driven into thermal runaway and explode. And a cascade of cell failures consumes that entire battery. Might look something like this. I have a feeling this is going to turn out slightly different than the other two illustrations. Oops. Anybody get any on them? No? We all good? Moving on. So to recap, an abuse event, reaction within the cell creates additional heat and gas and the reaction zone expands. Heat dissipation rate is substantially less than the heat generation rate over time. The cell enters thermal runaway. Additional heat and gas are produced. The cell violently vents and explodes. Additional cells are driven to thermal runaway, and cascade failure takes the entire battery with it. So, with such a rosy outlook, you have to ask yourself, that's as bad as it gets, right? If the previous information didn't complicate your electric vehicle workday sufficiently, then please allow me to humbly present my personal favorite, submerged vehicles. Where's the cursor? Here we go. Submarines present a different set of possibilities and a different timeline. They tend to bubble, and water entry may not deplete all of the stranded energy charge in that battery. Submerged vehicles can generate electrolysis gases as the battery arcs and shores. You may want to take steps to prevent those gases from accumulating if that vehicle's on the property. Roll down the windows, crack the deck lid, prop the hood open, give it a fighting chance. Once the waters recede, they can still be shock and thermal runaway hazards from vehicles that have been submerged. Simply because they've been in the water doesn't mean they have been quenched. And submarines in storage or under repair still need to be monitored for temperature and isolated when appropriate. You need to be watching any battery that has been compromised for its thermal state. So here's another stop where I'd say if we have any questions.
There's a couple here.
Sure.
It's for a while back. It says lithium and water don't mix, so adding water to an Li battery fire is recommended, with a question mark.
Yes, at the end of this, you will see that there were references to, there'll be reference pages. And this is a Massachusetts Fire Brigade along with MIT did all of the work on this by artificially heating batteries. They built bucks of what was shaped like a car, put a hibachi grill, if those of you that are old enough to remember those, or something underneath to artificially heat it, and then put several battery packs in the middle of it, and tried using class A, B, C, D, halon, anything else. It's not about water making contact with the lithium. At the point where it's already on fire, it's now about reducing the temperature. Yes, you will have reaction if you go along the lines of thought, like the guys on YouTube who take batteries like the one I held up and peel it and then drop it in a bucket of water. Sure, you'll get some flame reaction to it. But in the case of a lithium-ion battery fire from a performance vehicle, I hate to rag on Elon Musk, but his vehicles have the biggest batteries with the most oomph on the planet. When a Tesla fire starts up, the only way you're going to take that back down is reducing that thing's temperature. The only thing that has worked out so far, until somebody comes up with a different firefighting substance, is water.
Okay. The other one is there any push for an industry-wide certification recognized by manufacturers with high voltage systems, or is it still up to each individual manufacturer based on proprietary tools and tech?
Right now, it is my understanding that if you are connected at the hip as a dealer technician, you will be certified by that manufacturer. Whether or not ASE would be providing a sufficient industry certification, they have the L3, but I don't know if that dots all the I's, crosses all the T's, that would make all the manufacturers happy. This is a gray area question that I can't give you a good answer to. But as far as I'm aware, and my previous history was with Ford. As far as they were concerned, you weren't touching hybrid or electrics until you went through all of their courseware. If you had any outside certifications, really didn't matter to them. This is the case with most manufacturers, is that if you're working on our stuff, we want you trained in our methods and understanding our systems.
Yeah. I guess another one here was, I guess it's just it's about the volume of water to create enough of a heat sink, and right. So I guess that's what you said, is that's the only thing to cool it down, right?
Right. And while we're at it, think about it. If we're talking about a vehicle fire like a Tesla or anything else that's going to use a belly pan where the battery is and armor plated on the bottom, and then we will have the floor pan of the vehicle that isolates us from the occupants. So we have a layer of steel on the bottom, and we have a layer of molded steel on the top. And if a fire develops in between, unless we can stand the vehicle on its side, there's really no good way to cool that battery off. Unfortunately, that's the only thing that the resulting research indicated was, if you can lower the temperature, you will reduce the rate of heating and try and subside thermal runaway. If you allow it to self-heat, it will only go until it ignites, or if it hasn't already, and once it does ignite, it just continues to burn and continues to self-heat until it's consumed.
Last one, just more of a, you're not a car sales guy, but it says, why would I want an electric vehicle knowing this?
Because eventually they're going to come up. Right now, for the specific energy, or we'll go back to a better term that everybody understands, for the available energy density, lithium ion is the only player on the street. There are many, many places you can go on the internet, and they will tell you of, tales of greatness, of new battery technologies that are coming out, but none of them have hit the street as of yet. And right now in the Model 3 and the Model Y, we have a new lithium cobalt aluminum oxide battery that Tesla's bringing to the market. Why? Because it's the only thing that'll give him the performance value and at the same time hold enough energy to possibly be able to get from point A to point B more than 15 or 20 miles. The 300 miles, something comparable with gasoline. Eventually, somebody is going to come up with a chemistry that does not have the thermal runaway issue. Once that does, two things will happen almost instantly. That man will become a billionaire, because if it works and it's producible and it's clean and it's green, that will solve that problem so that we can start to use electric vehicles. They will come into their fruition. The second thing that will happen is I can stop giving this presentation, because more and more people will have realized that nobody's using lithium. It'll all be recycled into something else and not used for car batteries.
Okay, and that's the end of the questions for now. Oh, here's one more just popped in. Everything we have to power vehicles is combustible. Lithium is no different in my book.
Agreed. And it's like I said at the outset of this thing, this is not about bashing electric vehicles or a vehicle manufacturer. This is making educators aware, if they were not already, that there are some hazards. You may want to start teaching this. And all I'm trying to do is offer you some guidance on some things that we found out, things that we want to share, the things that we know about with you guys, so you can keep yourself safe and your students safe, and everybody gets to go home at night.
Okay. That's it now.
All right, moving on. So let's talk about personal protective equipment. Before you work with high voltage, you need the right high voltage personal protective equipment. And it's typical of things in the automotive world, they conflict with the rest of the world, because what we in automotive call high voltage, the personal protection equipment manufacturers, and that would be the guys that make PPE for linemen that work on high voltage wires going down the roadway. They call that low voltage, and in certain instances, ultra low voltage. Now, some of you may already have PPE that qualifies. You may not even know it. You may already have qualified shoes if they make ASTM 2413 11H for electric hazard, which simply states that when the boots are dry, and keyword here is dry, folks, EH boots must insulate the wearer, the occupant, from 18,000 volts at 60 hertz AC for 1 minute, or a continuous protection rating of up to 750 volts. Otherwise, your only option is the dielectric boot. The dielectric boot is a wonderful boot because it's rated for 20,000 volts, but it is not steel-toed, steel-shanked, no metatarsal guards. It's simply an overshoe, not crush-proof on any front. I throw this up here just so you understand what I was saying about the difference between high voltage and low voltage. The international, or just say the IEC, says that low voltage is from 120 to 1500 volts DC. Consider that in contrast that anything above 60 volts DC is considered high voltage in automotive. The reason I bring this up is because it's a cost issue. The higher the voltage rating on your personal protective equipment, although it may not look different from one piece to the next, it is. And if we are buying low voltage gloves, they are considerably less expensive than high voltage gloves. All qualified high voltage PPE will have a voltage range and an expiration date. This applies to the rubber products, gloves, boots, sleeves, aprons, all lineman PPE up to previous. And it's important to use the correct high voltage rating and to have your PPE recertified or replaced once it expires. We are not using any expired PPE. And in our case here, the class for that is class 0, 1000 volts AC, 1500 volts DC, and the color of the tag will always be red. So, rubber gloves will need to be inspected for surface defects. Air testing is the standard for integrity by roll-up testing or using a glove pump. I always recommend a glove pump. Under no circumstances should shop air be used or allow a student to test them or apply shop air to a glove. Once they do that, that glove is junk, in my opinion. Gloves can be pinholed by overinflation, and a pinhole is sufficient to convey a lethal shock. This all goes back to cost too, because you'll see later in the presentation our example of high voltage gloves that cost us $130 US. Now, if you're teaching high voltage full tilt, then a glove pump is a must. The task of testing is something you can delegate to a teaching assistant or a competent student. We want to test the gloves frequently to make sure nobody is using any compromised gloves. Make sure students are using the leather outers also to protect the inner rated voltage gloves. Outers need to be inspected for any damage or contamination. Why? Because at 400 to 600 volts, contaminants may be conductive, whereas at 12 volts, nobody would notice. If somebody decided they were going to do brakes or something else with high voltage gloves on, the outers, and had a little bit of grease and a little bit of shavings from the brake lathe, and happen to make contact and conduct a 12 volt circuit, it might be an oops or a giggle. At 600 volts, this could be a trip to the ER. If I was doing this in person, I would have samples of PPE to pass out among the group. Unfortunately, the photo is going to have to suffice. And there you see the Salisbury label. It is rated as class 0 up to 1000 volts AC. And also notice that they have expired long ago. We got them and they were 7 months expired when we took them out of the box. Now would be a good time to discuss PPE, which has an arc thermal protection value, or ATPV. These devices are essential for thermal isolation. Why? Because there might be an incident of arc flash. You need the right ATPV for your process and application. Once again, it's a case of make sure it's in the right range, above the minimum, but you don't need to go crazy, because you don't need to be spending money that you don't need to spend. Now, this chart shows the arc flash or hazard risk category as it relates to incident heat or incident energy, along with the minimum arc thermal protection value for that particular PPE. It must be noted here that the resistance to heat is not the same as electrical isolation. And in the case of education, I think you're going to find out that if you reach up the silo to your administrators and people that deal with safety, they would tell you at the minimum you're going to look at an arc flash category 2. That is a required arc rating of 8 calories per square centimeter. We'll get to that in a second. If I had my demo face shield to pass around, you would notice that it's a Cellstrom 31200. It's the only arc flash 2 rated protection we could find that isn't connected to a hard hat. Once again, they build most of the stuff for guys that climb up and work on long distance wire. It's arc class 2 with a thermal protection value of 9.9 calories per square centimeter. The ATPV rating is for protection against the incident of arc flash, not necessarily electrical isolation. And a calorie, as we all remember, is the energy required to raise 1 gram of water 1 degree Celsius at 1 atmosphere. That means absolutely nothing to me. It might to some of you. Or you might realize that the onset of a 2nd degree burn may occur at 1.2 calories per square centimeter. That's the Stoll curve. That goes back to the Navy in the 40s. But the best description I've ever heard for understanding is that 1 calorie per square centimeter can be approximated to holding your finger over the tip of a lit cigarette lighter over that flame for 1 second. Now, most institutions that require arc flash ratings will have you meet arc flash 2. And in the case of this face shield, the Z87 is for impact resistance only. It has nothing to do with electrical isolation or arc thermal protection value. So when we're discussing rated clothing, like this simple jacket pictured here, it's important to realize that for clothing to be ATP rated, it will inherently acquire a level of fire resistance, or better termed, flame resistance. Now, to maintain the minimum rating of this garment, it needs to be maintained or washed in a proper manner. At the same time, it's important to distinguish that while being arc rated makes an article fire resistant, being fire resistant doesn't necessarily make you arc rated. On the back of this jacket, that tag tells a story. We move in, the logo says that it's made by Magid and it is fire rated. But let's have a look at the inner tag, because this is where you're going to see, and this is where you need to watch in PPE, where is the fine print? And here it's telling you that it's machine wash only, do not use soap or soap powders, detergent, no chlorine bleach, no fabric softeners, tumble dry medium. An inner tag lays out the details. The ATPV is 10 calories a square. The garment is flame resistant, not flame proof. And the thing that killed me was that in the bottom, and you probably can't see it, that this garment is not explosion proof. I would have never thought that this garment was explosion proof, but my mistake. And as always, washing it incorrectly is going to be a problem because it's going to reduce protection value. As a best practice, don't use anything that is suspect. Inspect your personal protective equipment frequently, and probably the best practice of all is only use high voltage personal protective equipment for high voltage work. If you can afford it, segregate it, and this is the high voltage locker, and then everybody else can go for regular safety glasses and masks and whatever else you need to have. Face shields, if we're using a grinder, could be an entirely different set of tools. Now, if you are working on hybrid or electric as an educator, you're going to want one of these. You want one for each hybrid or EV being worked on. And what you're looking at is referred to as a lockout tagout box. Now, you can buy one on the web. They're not that expensive, or you can go over to the military surplus and buy a surplus ammo can, cut some holes in it. You could buy several of them and make it a project for students for extra credit. Need a minimum of 2 locks, one for yourself or for a teaching assistant, one that is not in the control of the students, and the other could be given to a student or a group of teams. And usually I would say teams, but right now it's probably a case of one student or a time or one team leader. You guys are going to have to figure that out because the COVID thing makes my head hurt. What you do with it is you store in things like the service plug, important fuses, the ignition keys or key fobs. On modern vehicles, you don't have a key fob or that coded ignition key. Nothing is ever going to happen to start that vehicle or get it activated to roll again. Anything that will disable the high voltage system. And the box doesn't open until you or a teaching assistant or some person in charge assesses the vehicle and decides it is now safe to try and reactivate this vehicle. Which means if you come up and you have orange wires hanging or tied in a knot because we think it's funny, you don't open the box. As far as test equipment, minimum rating is IEC Cat 3 or better at 600 volts. That's the minimum rating that we are recommending. You want to check your test leads frequently. Teaching assistant or competent student leader to check every voltage, every voltmeter test lead that's going out in the shop during electric work, or for EV and HEV work. Why? Because at 12 volts, a short, let's say we skinned a lead and we had exposed strands. At 12 volts, that exposed conductor would be an oops if it makes it to ground. You know, it'd actually be funny. You know, it's a little bit of an arc. Everybody gets a giggle, but everybody goes home. At 600 volts, that's a fire or we're calling an ambulance, and it doesn't take long. This chart shows the maximum transient voltage protection for working voltage range. Now, we said Cat 3. The reason we're saying that is because you can also get a Cat 2 and a Cat 1. What you're not gaining is the over voltage transient protection. That's why we want a Cat 3 at 600 volts. That gives you a minimum transient over voltage protection of 6,000 volts. So who here is teaching one-hand rule or live dead live? Veterans of high voltage work traditionally use the one-hand rule when working on high voltage circuits. This means that only one hand at a time can be used to work on a high voltage circuit. The purpose of this is to reduce the risk of electric current passing through the torso, causing cardiac arrest. This discipline with the PPE that you're already using is an extra layer of protection to prevent injury. To adhere to the one-hand rule when taking a direct reading on a high voltage circuit, is essential that you have at least one electrical lead that is equipped with an insulated alligator clip. And using one hand and one hand only, connect that lead with the alligator clip to one of the circuit's test points. And then taking that same hand, place the other lead in contact with another point to make a reading. No more than one hand should be holding a lead, touching the vehicle, or a ground at any time. A live dead live means using an alternate reference voltage to test your meter as part of the function for checking for 0 volts in things like system disconnection verification. We check the meter on the battery reference. If you're using a 12-volt battery or string 2 of them together to make 24 volts in a series, we test on the reference battery and then test the high voltage circuit for 0, and then immediately move back to the reference voltage to prove that the meter is still in correct function. Live test, dead test, live test. Meter should always be tested in the same range, so you may need to shut auto ranging off on some of your squirrelier meters. Just because NHTSA demands 500 ohms per volt system isolation doesn't mean that you don't need an insulation tester. There is no way to verify insulation isolation with a multimeter. Why? because if you can see the image, this particular fluke is showing 150 gigohms, but the reference voltage is 5,249 volts. Insulation testers are different animals compared to a multimeter. There's no way that a traditional multimeter can give you a reference voltage of 500 to 15,000 volts. So as we come to the close, every OEM that builds or sells in North America publishes an emergency response guide. They are geared towards first responders, but they can give you fundamental safety info like wires to cut if the 12-volt battery is inaccessible, where the service disconnect is located, where are the lift points, hopefully. Not all of them do, but some of them are coming around to, hey, if the battery's on the belly pan, where are the lift points? Where can I pick this thing up? Virtually every manufacturer has one available on the web. It takes a little bit of looking, but you can find it. So this is the reference list. National Renewable Energy Laboratories did Vehicle Safety Battery Guidance Roadmap by Dowdy and Parasam. And then when we were talking about crash safety of lithium ion, it was Isafani that did the study for Massachusetts Institute of Technology, and the National Fire Protection Association Alternative Fuels did the Emergency Field Guide for 2015. But if you need a book just about batteries and some of the quirks, Battery Hazards in Action, Accident Prevention by Levy and Bro. And before I give it up to questions, we only have a couple of minutes left, but I made it under the wire. Let me say it's not my intention to scare anybody off of electric drive, unless you plan on, of course, disregarding the hazards. There are a multitude of hazards. We want everybody to understand what those are, operate safely, and we feel that you should be fine if you're well informed. And with that, I'll say thank you and open it up to questions.
Okay, one's more of a comment here.
Mm-hmm.
Hybrid and EV safety and awareness should be part of the new basics covered in all programs.
Absolutely.
Another one is not using shop air because of the pressure or possible contaminants in the air.
Not using shop air because it, I'm sorry, please, was there more to that?
Well, there's another, would be able to put a pressure regulator down to something real low to control the amount of air while checking gloves.
It's going to be an expensive regulator because you're probably going to need to take your 140, or if you like to get the air impacts buzzing up at around 130 to 140 psi on a double lunger compressor, you're going to need 2 pounds maximum. The glove pump is infinitely more reliable, because what you do with the glove pump is you situate the glove on the pump, you pump it up, and you walk away. If in a set time, the pump manufacturer will often tell you as well, will the glove manufacturer, if it maintains for 5 minutes or 7 minutes or 10 minutes on the glove pump, that glove is good. A glove that falls down right away, we know that glove is junk. But it's the one in between that maybe doesn't make or hold for more than 3 minutes. There may be a micro hole in it, and that micro hole may be the difference if something's taking a path to ground. So yeah, you could devise a contraption if you wish, but you have to keep the pressure down. And I think it's going to be a maximum of 3 pounds. That may actually be a little high.
And then a question, do the gloves have an exchange or recycle value at all?
Probably not a recycle value, but gloves can be recertified by a lot of manufacturers that are selling them. If you are careful with your gloves, let's say if you had a expensive pair of gloves as the instructor that only you used, you could send them out. When you go to purchase, inquire about recertification. What's their policy? They may have a high line of gloves that's more expensive, but they can probably get you recertified for a nominal fee, and you have to do the math because there are a myriad of glove manufacturers out there. But I imagine that there are guys that will recertify for a nominal cost. That means that you're not spending for a new pair of gloves until somebody screws the pooch, excuse my French, and puts a hole in that glove. Now that glove is useless.